Last time we talked about perpendicular bisectors, and today we're going to be talking about angle bisectors in triangles. So just as a reminder, an angle bisector is a ray that divides an angle into two congruent angles, so it divides it in half. The second thing to remember is that the distance from a point to a line is the length of the perpendicular segment from the point to the line. So if you look at this picture here, we have an angle QPR, and we see that ray PS is an angle bisector because it divides this angle into two congruent angles, so QPS and SPR are congruent to each other. And then we also see here that there is this point S, and we draw the distance from point S to each side of the angle by drawing that blue line. So you can see that that blue line is perpendicular to that line from that point. So here's the angle bisector theorem. If a point is on the bisector of an angle, then it is equidistant from the two sides of the angle. So what this is saying is, if you have point D and it's on the bisector of the angle, so AD is in fact the bisector of this angle here, then that point D is the same distance away from the two sides. Remember that the distance is that perpendicular line from the point to that line. So that means BD and CD are congruent to each other. Now the converse of this theorem is also true. So if a point is in the interior of an angle and it is equidistant from the sides of the angle, then you know that it lies on the bisector of that angle. Here is a picture. So this is saying that if you have some point D and you know that it is the same distance away from B as it is to C, then you also know that D must be on the bisector of the angle. You know that AD must then bisect the angle. Looking at example 1, this says find the measure of angle GFJ. And here you can see that this point J is the same distance away from G as it is from H. And you can see those are perpendicular segments. So because you know that J is the same distance away from both sides of the angle, you then know that J must be on the angle bisector of this angle, which therefore means that JFH is 42 degrees, and so GFJ must also be 42 degrees. So we use the converse of the angle bisector theorem here. We said, well, if we know that J is the same distance away from both sides of the angle, that must mean, therefore, that J is on the angle bisector. And if it's on the angle bisector, that tells you that angle GFJ must be equal to angle HFJ. All right, example 2. A soccer goalie's position relative to the ball and goalposts form congruent angles as shown. Will the goalie have to move farther to block a shot toward the right goalpost, R, or the left goalpost, L? Now, the congruent angles that you see there, marked in red, that lets you know that the goalie is in fact on the angle bisector of angle LBR. Now, using the angle bisector theorem, that must mean that the goalie is the same distance away from R as it is from L. So that tells you that, well, does the goalie have to move farther to block a shot towards the right or the left? It's going to be the same either way. Example 3. For what value of x does P lie on the bisector of angle A? So here you can see a point P, and you can also see that PB and PC are drawn in there. Now, in order for P to lie on the bisector of angle A, you know that P must be the same distance away from AB as it is to AC. In other words, BP and CP must be equal to each other. So we are going to go ahead and substitute. So we have x plus 3 equals 2x minus 1, which gives us x equals 4. So we can say that point P lies on the bisector of angle A when x equals 4. All right, we have another theorem. This one is talking about the concurrency of the angle bisectors in a triangle. So this says that the angle bisectors of a triangle intersect at a point that is equidistant from the sides of the triangle. And we call that point of concurrency the incenter. Okay, so here is a picture. We have triangle ABC, and it says that the angle bisectors of a triangle, so those are the lines that are drawn in red, so AP, BP, and CP, those are the angle bisectors. They intersect at a point P that is equidistant from the sides of the triangle. So point P is the same distance away from AB as it is to BC as it is to AC. So in other words, if you draw a line from that point to the line perpendicular to that line, so that means PD, PE, and PF that are drawn here, those are all equal to each other. Let's take a look at our last example. In the diagram, N is the incenter of triangle ABC. Find ND. So by the theorem that we just went over, we know that the incenter, N, is the same distance from each of the sides of triangle ABC. That means ND, NE, and NF are all equal to each other. Now, since the measurements that we do know are given here at NA and AF, and we know that NF is perpendicular to AF, we know that we have this right triangle, NAF. So if we look at that right triangle, we know we can apply the Pythagorean theorem to find the distance from N to F. So using the Pythagorean theorem, we have 20 squared equals NF squared plus 16 squared. And we can go ahead and simplify this, and we get that NF is equal to 12. Now we found NF, but since N is the incenter, we know that NF, NE, and ND are all equal to each other. So if we found NF is equal to 12, that means ND must also be equal to 12.